Over the last few lectures, we have been talking about the original attempt to get a version of quantum mechanics which is consistent with the special theory of relativity. This, of course, is none other than the Klein-Gordon equation, which, let me remind you, though named after Klein and Gordon, was actually originally envisaged by none other than Schrödinger himself. Now, this particular attempt did not really work very well as a theory of single particle quantum mechanics. Now, based on the lessons that were learned from this attempt, Dirac formulated another equation which was not perfect as an equation for a single particle quantum mechanical system, but did much better at this than the Klein-Gordon equation did. So let me just remind you quickly about the lessons that were learned from the Klein-Gordon equation. Now, the first thing that we learned is that any relativistic free particle wave function must satisfy the Klein-Gordon equation, because that's nothing but the embodiment of the relationship E square equals E square C square plus M square C to the 4. So this is the relationship between the energy and momentum of a relativistic particle, and any equation which claims to be relativistic must ultimately satisfy this equation, box plus M square C square over H cross square acting on psi is 0, where box is the familiar D'Alembert operator, 1 by C square del 2 del T2 minus Laplacian. Now, one of the problems that the Klein-Gordon equation led to was the existence of negative energy solutions. As we will see later, this problem actually persists with Dirac's equation. However, Dirac found out a very novel way of getting around this particular problem, and indeed that problem led to a wonderful new opportunity and a new discovery, that of antiparticles. But we are going to talk about that later. The other basic problem that the Klein-Gordon equation had, apart from this negative energy solution problem, was that it did not admit of a quantity which could be interpreted as a valid probability density. In particular, it did have a quantity like rho in the Schrödinger equation, which turns out to be a conserved quantity over time, whose integral turns out to be a conserved quantity over time. However, this rho was not positive definite. And the fact that the rho was not positive definite could be traced back to the fact that the equation, this Klein-Gordon equation, happens to be a second order equation in time, and therefore it allowed you to choose rho and del rho del t, the first time derivative, independent of each other, and as a result, you could possibly come up with initial configurations which would admit of non-positive definite values for rho. So the fact that the Klein-Gordon equation was a second order equation actually was problematic. What Dirac realized is that if we could find an equation like the Schrödinger equation, which was first order in time, you could get rid of this problem. Of course, we already know of one version of a quantum mechanical equation which is first order in time, and that is none other than the Schrödinger equation that we all know and love. However, the Schrödinger equation is first order in time but second order in space, and this is not a problem because the Schrödinger equation, at least in this particular version, is clearly an equation for a non-relativistic system. On the other hand, if we want an equation which is relativistically covariant, what we must have is the symmetry between space and time. So if it is first order in time, you would also have to demand that it be first order in space. So you should have first order time derivatives as well as first order space derivatives. So what Dirac did was start off by assuming that you do have such an equation and model this more or less on the Schrödinger equation. So he wrote IH cross del psi del t on the left equals H cross C by I alpha j del del x j of psi summed up over all j from 1 to 3. So basically, if you remember that h cross by I del x is actually the momentum operator, this is really very much like the momentum times c, but with some dimensionless extra factors alpha 1, alpha 2, alpha 3 thrown in. In addition to that, you have beta times mc square psi. You expect an mc square in the energy. After all, IH cross del psi del t should give you, in the stationary state limit, the energy times psi, and one piece of the energy should be the rest energy mc square. So you do expect something which looks like mc square psi, but once again, because you have this demand that this equation must be consistent with the Klein-Gordon equation, Dirac threw in an extra factor of beta. Aim now was to find out these quantities beta, alpha 1, alpha 2, alpha 3, or at least find out basic properties governing these objects, so that the aim now was to find out these objects beta, alpha 1, alpha 2 and alpha 3, or at least to find out basic properties governing these objects, which would ensure that this equation would imply the Klein-Gordon equation. Just one word about the notation before we proceed. You must have noticed that I have written alpha j with j as a superfix. This of course is not a power, it's just the index just written upstairs. And the reason behind this is that we are going to extensively use Einstein's summation convention later, although here we are not doing that, we are explicitly writing down the sum over j going from 1 to 3 in these equations. But later on, we will be able to economize our notation a lot by dropping the sigma. But there, in the Einstein convention for special relativistic situations, we have this rule that a repeated index is summed up, but only if it occurs once as a superfix and again as a suffix. In anticipation of that, what we have done is we have written alpha j with a superfix. Remember del xj with effectively, so to speak, xj in the denominator actually is equivalent to having a lower index or a suffix. Or more technically, del xj actually transforms like a covector component. Okay, let us proceed with trying to get this to match the Klein-Gordon equation. The Klein-Gordon equation, of course, is second order in both space and time. So, because you have IH cross del psi del t on the left of our assumed equation, what you need to do is apply this twice. So, IH cross del t applied twice on psi will, of course, give you minus h cross square del 2 psi del t2. On the other hand, what this is equal to, on the right, is the operator h cross c by I sum over j alpha j del j plus beta mc square acting twice on psi. And because we have to be careful about repeated summation indices, I've changed the summation index in the second term to k, although as long as the brackets are there and you're clear what is being summed up, that's not really necessary. It will become necessary in the next step when we actually open this out completely. And opening this out simply gives you h cross square c square alpha j alpha k del j del k. Note that alpha j's are objects which are there in the equation. The only thing we are positing about them right now is that they are independent of space and time. So the partial derivative operators can happily travel through them. And what you have is alpha j del k summed up over all values of j and k. So that's a quadratic term. In addition, you have the term which you get by multiplying the alpha j del j term in one factor with the beta mc square in the other. Of course, here multiplying really means apply one after the other. And here we have to be a bit careful about the order in which we are applying things. We are not so sure at this stage that alphas can be numbers. In fact, we will soon see that they cannot be. So we are not going to assume that they commute among each other. So being careful about that gives us alpha j beta plus beta alpha j from the two factors. And finally, you have beta square m square c to the 4 as the final term in your operator. This is acting on psi. What you want to ensure is that the resulting equation becomes exactly the same as a Klein-Gordon equation. To make the connection with the Klein-Gordon equation even clearer, what I have done next is divide through by h cross square c square and move the second derivative with respect to time to the other side. So now you have 1 by c square del 2 del t2, which is basically this term moved to the other side, after division of course by h cross square c square. This one stays as it is except that the h cross square c square has gone away. Here what you have got is mc by h cross times 1 by I times alpha j beta plus beta alpha j times del del xj. Although I did not say so explicitly so far, I am pretty sure everybody understood that del small j is shorthand for del del xj. Plus beta square m square c plus 4 by h cross square psi. Let us compare this now with the Klein-Gordon equation. The Klein-Gordon equation is 1 by c square del 2 del t2 minus Laplacian plus m square c square by h cross square acting on psi equals 0. Note that if you look at these two equations together, it should be obvious that beta square must be equal to 1 or something which is equivalent to 1, so that you recover this term in the Klein-Gordon equation. Now what about this term? This term involves a first order derivative with respect to x, y and z. Of course, there is a sum over all j here, but there is no such corresponding first derivative term in the Klein-Gordon equation. So if you want this equation to be equivalent to this, you must demand that alpha j beta plus beta alpha j is 0. This will get rid of the linear term. Now the quadratic term Laplacian here and alpha j alpha k del j del k summed over all j and k here, these two must match each other. And now you have to be a bit careful in the sense that del j del k is actually symmetric in j and k. If you were to interchange j and k, it would become del k del j, but mixed partial derivatives commute, so it does not matter whether it's del j del k or del k del j, they are both the same. So this term really is actually equal to alpha k alpha j. I am just not writing the sum here, but you should understand that that's there. This is just relabeling the indices j and k. I've switched j and k with each other, but note that since del k del j is the same as del j del k, of course there's a minus sign in front, this is minus alpha k alpha j del j del k as well, or equal to minus half alpha j alpha k plus alpha k alpha j del j del k. What you have in the Laplacian on the other hand is actually delta ij del I del j. Remember, only diagonal terms del 2 del x2 del 2 del y2 and del 2 del z2, or of course you could just as well write this as this thing with instead of j and k you could have written I and j here. Now what is important is since del j del k is symmetric in the interchange of k and j, only the symmetric coefficients of both sides can match. Any antisymmetric part when contracted with del j del k would give you 0. Which is why you could not actually equate alpha k alpha j here or alpha j alpha k here with the delta jk, which would have multiplied delta j delta k in this expression. What you would have to do is symmetrize this first and only equate the symmetric part to delta jk, or if I wrote this with I and j instead, I would have equated that to delta ij. With that in mind, what we get is alpha j alpha k plus alpha k alpha j is twice delta jk. So these are the basic properties which we are demanding of our objects beta and alpha, and only when these are satisfied will our first order equation in space and time be equivalent to this to the Klein-Gordon equation. Let us now see exactly what these demands say about the objects beta and alpha 1, alpha 2, alpha 3. Now the first thing that we see from these equations is the following. We would have loved the quantities alpha 1, alpha 2, alpha 3 and beta to be numbers, but that simply will not work. Beta square equal to 1 would immediately imply that beta is not 0 if we are talking of numbers, and that would lead to the statement that alphas would have to be 0. But if alphas were 0, you would not be able to satisfy the last demand. So numbers simply won't do. If not numbers, what can they be? The Dirac tried the next obvious choice, square matrices. And of course, then you would have changed your interpretation of the wave function. Instead of a single function, it would have to become a column vector. Or if it's an n by 1 column vector, that's equivalent to n independent functions. So rather than systems which are described by a single wave function, as we had seen in non-relativistic quantum mechanics, here we are going to have many functions rolled together in a single column vector. Thankfully, there is not so much of a novelty. After all, when you talk about spin half particles, even in the non-relativistic context, we have to talk about two-dimensional column vectors, or actually two wave functions rolled into one. So having multiple wave functions rolled into one single column vector is not really that much of a surprise. But then you would want your equation, especially the right-hand side of your basic equation, to involve a Hermitian operator. After all, the eigenvalues of this operator should really be the energy, and you don't want the energy to be complex. So you would want the right-hand side of the equation that you wrote down to be Hermitian, and one part of the demand would be beta and alpha 1, alpha 2, alpha 3. All these four matrices must be Hermitian matrices. And of course, that would mean that you would have to change certain things. Beta square can no longer be the number one, it has to be the identity. Similarly, alpha k plus alpha j is not just the number twice delta jk, it has to be twice delta jk times the corresponding identity. Now, beta square equals the identity matrix immediately implies that the squares of the eigenvalues of beta must be equal to eigenvalues of I, which are of course only 1, which means beta's eigenvalues have to be plus 1 or minus 1. Now the last of our demands, alpha k plus alpha j is twice delta jk identity, specialized to the case where j and k are both equal to I, would simply read alpha I square is also identity for each one of the i's. That means for any I, the matrix alpha I would also again have eigenvalues of plus 1 and minus 1. So all possible eigenvalues of the four matrices we are looking for are either plus 1 or minus 1. If you now take a look at our second equation, the statement which now says that the matrices alpha j and beta anticommute, and multiply by beta on the left, on both sides, what you are going to get is beta alpha j beta plus beta square alpha j equals 0. And since beta square is the identity, this simply is the statement that beta alpha I beta equal to minus alpha I. Now, this leads to a very important conclusion. If you take the trace of both sides of this equation, what you get is trace of beta alpha I beta is trace of minus alpha I. Now, trace of a negative of a matrix is simply negative of its trace. So, the right hand side is simply minus trace of alpha I. On the other hand, you can simplify the left hand side, trace of beta alpha I beta, by using the property known as cyclicity of trace. What that means is that you can bring the beta from here to the front. So that gives you trace of beta square alpha I is equal to minus trace of alpha I, but beta square being the identity, this tells you the trace of alpha I must be minus trace of alpha I, and hence alpha i's trace must be 0. In fact, you can also do a very similar calculation by multiplying beta alpha I plus alpha I beta equal to 0 by alpha I instead of by beta, and conclude using that trace of beta must be 0. But now, notice that if the trace is 0 of a matrix, so the eigenvalues are only plus 1 or minus 1, then among the eigenvalues you must have equal numbers of plus 1 and minus 1. Otherwise, you will not be able to get a 0 trace. Let me just remind you, trace of a matrix is the sum of its eigenvalues. And thus, the total number of eigenvalues must be even. So these matrices must be even dimensional matrices. Other useful results that will immediately follow, in fact one of them I've already talked about, trace of beta is 0. Trace of beta alpha I is 0 is actually trivial from our demand that beta alpha I plus alpha I beta vanish. And of course, in addition to that, you have to use cyclicity of trace. If you use cyclicity of trace after taking the trace of the equation alpha I alpha j plus alpha j alpha I equals twice delta ij times the identity, what you would get is twice trace of alpha I alpha j on the left hand side. And okay, I've made a mistake here. This really should be d delta ij. When I had written this down, I had forgotten that there is an extra 2 in the anti-commutation relation. We had a twice delta ij times the identity. That 2 cancels out this 2. D here is nothing but the trace of the identity matrix, and D of course is nothing but the size of the matrix, which as we have already seen must be an even number. Now this actually is very useful in establishing this rather important result, that the set of matrices beta alpha 1 alpha 2 alpha 3 is a linearly independent set. To show that, what we need to assume is that you could combine them linearly with coefficients b, a1, a2, a3 to get 0, the null matrix, and show that this would imply that all these coefficients b, a1, a2 and a3 must be 0. I'm just going to show you that b is 0. The proof that a1, a2, a3 are 0 is very similar. So all you need to do is multiply both sides of the equation by beta. I've done that on the left. You could also do that on the right. It will not really matter. But that will give you b beta square plus a1 beta alpha 1 plus a2 beta alpha 2 plus a3 beta alpha 3 equal to 0. Note that beta square is the identity, whereas beta alpha 1, beta alpha 2, beta alpha 3 are all traceless matrices. So if you take the trace of both sides, what you will get is b times trace of the identity, which is of course capital D, plus 0 from all the other terms, must be equal to 0. And since the dimensionality of the matrix is not 0, you must conclude that b is 0. The proof that a1, a2 and a3 are 0 follow in the very similar fashion. So let me just quickly sum up what have we learned so far. We have learned firstly that the quantities that we are looking for, beta, alpha 1, alpha 2 and alpha 3, are not numbers. We are hoping that they are matrices at this stage. Unless we can find explicitly matrices which will satisfy the demands, we cannot be sure. But as we will soon see, we will succeed in finding such matrices. Now, what kind of properties do these matrices have? Each one of them squares to the identity, has eigenvalues plus 1 and minus 1, has trace of 0, and hence they are traceless Hermitian matrices. And we have also established, and from this we have established that they are even dimensional. So what we are looking for are 4 even dimensional traceless Hermitian matrices which satisfy our basic demand. The question now is, do such matrices at all exist? And if they do, can we find them? Let us start the search at the smallest possible dimension. Since the dimension has to be even, as we have seen, we are looking now at two-dimensional matrices. So let me remind you what we want are 4 2x2 traceless Hermitian matrices which satisfy the basic conditions that we had written down about the anti-commutation and all that. So note that in 2D, any traceless Hermitian matrix can be written in this very simple form. Here x, y and z are real numbers. A Hermitian matrix must have real elements on the diagonal, and because it's traceless, the two elements have to be negatives of each other. So what we have are z and minus z. The two off-diagonal elements must be complex conjugates of each other. So if you write one of them as x minus iy, with x and y being real, the other one has to be x plus iy. This form should be very familiar to all of you, because all we are saying here is that, because this is possibly the way in which you were introduced to sigma matrices. Or maybe you were just told that the sigma matrices are sigma 1, sigma 2, sigma 3 given by 3 specific matrices. But notice that any general traceless Hermitian matrix can be written down as x times 0, 1, 1, 0 plus y times 0 minus I 0 plus z times 1, 0, 0 minus 1. Of course, you would recognize this as x times sigma 1 plus y times sigma 2 plus z times sigma 3. And this is shortened or abbreviated to the expression r vector dot sigma, where r vector of course is x, y, z, the position vector, or something which looks like a position vector at least, and the sigma vector is just a way of saying that we have three matrices, sigma 1, sigma 2 and sigma 3. So as we can see, all 2x2 Hermitian traceless matrices can be written down in terms of three basis vectors, so to speak. Sigma 1, sigma 2, sigma 3 are the basis vectors here, with three arbitrary real coefficients x, y and z. And this means that the space is three-dimensional. That of course is troublesome for us. We cannot accommodate four independent matrices that we want. Remember, we want beta, alpha 1, alpha 2 and alpha 3, and four linearly independent matrices cannot exist in a three-dimensional space. So, two dimensions don't work. We must go over to 4D. But before I do that, let me remind you that we need four matrices simply because we are in three-dimensional space. If we were working in 2D space plus one time, then three matrices would have sufficed, and you could have used the sigma matrices for this purpose. Indeed, if you want to study relativistic quantum mechanics in 2 plus 1 dimensions, you already have all the necessary ingredients here. You don't even need to learn something new. All you would have to use is your nice and familiar sigma 1, sigma 2, sigma 3 matrices. Sigma 3 could take the place of beta, and sigma 1 and sigma 2 could take the place of alpha 1 and alpha 2. In fact, the Dirac equation in 2 dimensions, 2 plus 1 dimensions, happen to be very, very important nowadays in condensed matter physics, because it gives us a very nice way of explaining features of the material graphene, which, as you may be aware, is the hot material nowadays. Anyway, that's an aside, because we are more interested in relativistic quantum mechanics in 3 plus 1 dimensions. So we will move over to 4 by 4 matrices and try to see whether we can find beta, alpha 1, alpha 2 and alpha 3 which satisfy our basic demands. Before we proceed on our quest, let me point out a very important thing. Suppose we do manage to find out 4 matrices beta and alpha I with I running from 1 to 3 which satisfy our basic demands. What we can then do is the following. We can carry out the same unitary transformation on each one of these matrices. Remember, a unitary transformation is just a similarity transformation with the matrix carrying out the transformation being unitary. So U dagger is U inverse. You can easily check that the resulting new matrices beta prime, alpha prime 1, alpha prime 2 and alpha prime 3 will each be traceless and Hermitian, and what is more important for us really is that they will also satisfy the basic conditions that we had laid down, Dirac's basic conditions. What this means is that if you find one set of 4 matrices which satisfies the equation, you can find infinitely many such matrices just by carrying out a unitary transformation. This of course tells you that your solution cannot be unique. If there's one set which satisfies, you will have infinitely many such sets. But this actually is an advantage because we can use this to make our life a lot simpler. What we can do, for example, is by carrying out this unitary transformation, you can diagonalize one of these 4 matrices. We choose to diagonalize beta to begin with. Now, we already know that the 4 eigenvalues of beta, 4 because we are dealing with 4 by 4 matrices now, have to be 1, 1, minus 1 and minus 1. So in a basis in which beta is diagonal, the form of beta is already fixed up to a reordering. But it's obvious that I can have a basis in which beta will have this form. 1, 1, minus 1, minus 1 down the diagonal. And for convenience in what is going to come, I'm going to write beta in this block form where we break up the 4 by 4 matrix into 2 by 2 blocks with identity and minus identity sitting in the diagonal positions. These are of course 2 by 2 identities and 2 by 2 null matrices sitting in the off diagonal position. Let me stress once again that beta does not have to be this way, but we can always find a basis in which beta looks like this. What about the other 3 matrices? Now, let us begin with the fact that each and every one of them alpha matrices anti-commute with beta. For ease of calculation, what we have done is we have broken up a typical 4 by 4 matrix, we are calling it alpha now, into 2 by 2 blocks, A, B, C and D, where each of these are actually 2 by 2 matrices. And then we can use the standard rules of matrix multiplication to calculate the 2 products alpha beta and beta alpha. The sum of these 2 products must be 0. Now notice that if I add up alpha beta and beta alpha as shown, you can easily convince yourself that those expressions are correct. But if you add them up, the off diagonal pieces simply cancel. In the diagonal places you are left with twice A and minus twice D. Note that since alpha beta plus beta alpha have to be 0 for our alphas, A and D, the diagonal blocks must vanish for our alphas. So, a typical alpha I must take this particular form. Null matrices, 2 by 2 null matrices on the diagonal and an off-diagonal block of xi on the top right corner would have to be accompanied by its adjoint on the bottom left corner, simply to ensure that this matrix alpha I is Hermitian. So, although the general matrix could have independent blocks B and C, for Hermitianity you must have xi and xi dagger, where x1, x2, x3 are 3 2 by 2 matrices. We now need to find out conditions which x1, x2 and x3 will obey. And the obvious place that we should look at for this is the anti-commutation relation obeyed by the alpha i's. Now with alpha I taking this form, one such matrix for each I, it is easy to see that alpha I, alpha j, the product, will actually have a block diagonal structure with xi, xj dagger, this 2 by 2 matrix on the top corner and xi dagger xj in the bottom corner. Of course, being block diagonal, there will be zeros in the off diagonal block positions. Alpha j, alpha I you don't really have to work out again. All you have to do is swap I and j, the two indices, to find out what alpha j alpha I is going to be. We can then exploit our final Dirac condition, alpha I alpha j plus alpha j alpha I equals twice delta ij times the 4x4 identity matrix to give you these relationships between xi and xj. Xi xj dagger, which you get from alpha I alpha j, plus xj xi dagger, the corresponding term from alpha j alpha I, must be what is sitting on the top diagonal block of twice delta ij I4, that is, it must be twice delta ij times I2. And looking at the lower block, you also get xi dagger xj plus xj dagger xi is equal to the same thing. So we now have a bunch of relationships which xi's must satisfy to ensure that we do have matrices which satisfy our basic Dirac conditions. Now this is still quite a hard task, but this can be simplified considerably by making an assumption. Let's just choose all our xi's to be Hermitian. This was not necessary, it's just a choice that we are making at this point to simplify our calculation. If I do that, then both of the demands that we have, the one coming from the top left corner and the other coming from the bottom right corner of the alpha I alpha j plus alpha j alpha I matrix, boils down to the same demand. Xi xj plus xj xi is twice delta ij I2. This is great because we already know of 3 2x2 matrices which do satisfy this particular anti-commutation relation. There are no prizes for guessing what they are. They are none other than our old friends, the sigma matrices. Remember, sigma I sigma j plus sigma j sigma I is twice delta ij times the 2x2 identity. So at least what we have done is we have established that one solution exists, and because of this unitary transformation possibility, that immediately implies that infinitely many solutions exist. That solution, written down in the form of 2x2 matrices, is simply this. Beta is I2 0 0 minus I2, which is just another way of writing the 4x4 diagonal matrix with 1 1 minus 1 minus 1 down the diagonal, and the 3 alphas are given by alpha I equals 0 sigma I 0. So in the end, what we have found is at least one solution exists for the Dirac conditions, which are actually built up out of pretty familiar matrices. The sigma matrices play their role once again in physics. Now that we have managed to convince ourselves that the Dirac equation exists, that is to say, it is possible to find 4 objects beta, alpha 1, alpha 2 and alpha 3 which satisfy the basic Dirac demands, let us now turn to the question of what does this at all mean? What is the physical significance of this psi, which now, remember, has to be a 4x1 column vector or 4 functions rolled into one column vector. Now, one of the first things we would want to do is to see whether we can overcome the stumbling block that we had with the Klein-Gordon equation, that of a non-positive definite, or at least not necessarily positive definite, probability density. So, can we find out a probability density from the Dirac equation which does not suffer from this problem? So, to see this, we start from the Dirac equation once again. Since this is the first time we are going to handle the Dirac equation in a mathematical calculation, let me remind you that both sides of this equation happen to be 4x1 column vectors. Del psi del t, of course, is the derivative of a 4x1 column vector, which is by itself a 4x1 column vector. On the right hand side, you have the matrices alpha and beta, which are 4x4 matrices, acting on 4x1 column vectors, either spatial derivatives of psi or psi itself. Now what we do next is multiply this equation on the left by the row vector psi dagger. This is a perfectly legitimate operation. Psi dagger can multiply a 4x1 column vector, and you are left with this equation, IH cross psi dagger del psi del t plus h cross c by I sum over j equal to 1 to 3 psi dagger alpha j del del xj plus mc square psi dagger beta psi. What we do next is take the adjoint of this equation. Not the Hermitian adjoint at the operator level, but just a matrix level adjoint. And all we need to do is use the fact that when you take matrix adjoints, the order reverses. AB dagger is B dagger A dagger. That immediately shows that on the left we will have minus IH cross. The minus sign simply comes from I being conjugated. And del psi del t coming to the front but being adjointed, so that's del psi dagger del t. And psi dagger going over to the back, but adjoint of psi dagger is psi. So you get minus IH cross del psi dagger del t psi. And a very similar thing happens on the right hand side. The mc square psi dagger beta psi rather obviously is Hermitian, so it does not change. Whereas the term with the spatial derivatives, this sum over the 3j's, changes sign because of the I in the denominator there. And when you reverse the order of the matrices involved, you get del psi dagger del xj on the left, alpha j dagger in the middle, and psi on the right. Alpha j dagger, of course, is the same as alpha j because the alphas are Hermitian. So this is what we end up with. Now, as you can see, there are terms here which involve derivatives of psi, either with respect to time or with respect to space. And there is one term which does not depend on a derivative. And it's very easy to get rid of this term simply by subtracting the two. And if you do that, you end up with this expression. Now, why did we really want to get rid of the non-derivative term, so to speak? The answer is we are looking for the continuity equation. And in the continuity equation, you actually have del rho del t plus divergence of j equals 0. Each and every one of the terms have some kind of derivative or the other. As you can easily see, the term on the left that you have now is a derivative. It's a time derivative of psi dagger psi. And it will take only a slightly bit more thought to see that there is a divergence sitting on the right hand side. If we cancel through with the IH cross and bring everything to one side, the equation simply becomes del del t of psi dagger psi plus c times sum over j equals 1 to 3 del del xj of psi dagger alpha j psi. And this is obviously a divergence. It's a divergence of a 3-component object with psi dagger alpha 1 psi, psi dagger alpha 2 psi, psi dagger alpha 3 psi. Remember, psi dagger alpha 1 psi, etc. are all numbers. So we have 3 numbers sitting together, and that of course is what we would call a vector. This then takes the form of del rho del t plus divergence of j equals 0. Here rho happens to be psi dagger psi and j happens to be a vector which in vectorial notation can be written down as c psi dagger alpha vector psi. Of course, alpha vector is really a collection of these 3 matrices, alpha 1, alpha 2 and alpha 3. As I have already said, each of the components of j, c psi dagger alpha I psi, are actually numbers. Not only that, they are actually real numbers, as you can easily check by simply taking their adjoint. These are all self-adjoint objects, and because they are numbers, they have to be real numbers. Coming to rho, the so-called probability density, at least something to which we want to ascribe the role of a probability density, we see that not only is rho a real number, it's actually always positive definite. Remember, psi dagger psi, if you were to write that in terms of the components of psi, would simply be psi 1 mod square plus psi 2 mod square plus psi 3 mod square plus psi 4 mod square, which of course can never be negative, In fact, the only way rho can be 0 is if psi itself vanishes. In that sense, this rho has a lot in common with the rho that we use in the Schrodinger equation. There, of course, psi is just a complex valued function and the rho is psi mod square. Here, our psi is a complex valued vector function, that is, 4 complex functions rolled into one column vector, but psi dagger psi is a real positive number. Let me remind you that the equation del rho del t plus divergence of j equals 0, the so-called equation of continuity, actually implies that the integral of rho over all space is conserved. And this actually means that we have a very nice way of interpreting psi dagger psi as a density of a probability for the particle to be directed somewhere, just like we did in the non-relativistic case. So at least one of the major stumbling blocks which the Klein-Gordon equation suffered from, the non-existence of a positive definite probability density, has been tackled here. The Dirac equation has this advantage that it admits of the density of a conserved quantity, which we can interpret as a probability density, simply because it never becomes negative anywhere. So in this sense, Dirac equation definitely scores 1 over the Klein-Gordon. It does not suffer from one major problem which the Klein-Gordon suffered from. But let me remind you that the other major problem with the Klein-Gordon equation was the existence of negative energy states. Is the Dirac equation free of them? In order to see that, let us just quickly look at a solution to the Dirac equation, a solution corresponding to a particle at rest, and see what kind of energies a particle at rest should have. If you have a particle at rest, its wave function can depend on time, but will not have any spatial dependence. Remember, derivatives with respect to x, y, z essentially talk about the momentum of the particle in the x, y, z direction respectively. So a stationary particle would not have any spatial dependence in the wave function. Now, in that case, the Dirac equation reduces to IH cross del psi del t equals beta mc square psi. The other terms involving alpha have just dropped out because del psi del x, del psi del y and del psi del z are 0. Now, in this particular representation, beta is a diagonal matrix with 1, 1, minus 1 and minus 1 as the diagonal elements. So, you can very easily rewrite this equation, the Dirac equation for the particle at rest, in terms of the 4 component wave functions. It is very easy to see that what you will get is IH cross del psi 1 del t is mc square psi 1, which translates to del psi 1 del t equals minus I mc square by h cross times psi 1. You actually get a similar result for psi 2, psi 3 and psi 4. But the important point to note is for psi 1 and psi 2, the factor in front is minus I mc square by h cross. For psi 3 and psi 4, the factor in front is plus I mc square by h cross. And it's very easy to find out the solutions to this bunch of equations. And it's also very easy to figure out that we have 4 independent solutions. For example, the first one of the solutions is one in which we have kept psi 1 non-zero and all the rest 0. And we have taken the initial value of psi 1 to be 1. In such a case, psi 1 would of course evolve with a factor e to the minus I mc square t by h cross, and we end up with this particular column vector as our first independent solution. Note that I have written the label 1 inside a bracket just to distinguish it from a component. However, there is an intimate connection between which component is non-zero in this notation and which particular solution are you talking about. For example, psi 2 will have only the second component non-zero, all the other components 0. And it will also have a time-dependent factor of e to the minus I mc square t by h cross. Now, this factor of e to the minus I mc square t by h cross should be very, very familiar to all of you. In non-relativistic quantum mechanics, we have all seen that energy eigenstates pick up phase factors which are given by It is a minus IET by H cross. And so the first two solutions that we have here are simply solutions with energy given by mc square. And that is perfectly consistent with the fact that we are dealing with particles which are at rest. Their energy is just the rest energy mc square. The third and the fourth independent solution are the ones in which the third component and the fourth component respectively are the only ones which are non-zero. The important point here is the prefactor which dictates time evolution in these two cases is given by I mc square t by h cross in both cases. There's a plus I mc square t by h cross in the exponent, and that rather obviously corresponds to an energy of minus mc square. So of the four independent solutions for the Dirac equation for a particle at rest, two correspond to positive energy solutions, two others correspond to negative energy solutions. Plus mc square for the positive energy particles, just the rest energy, and minus mc square for the negative energy particles. So what we find here is this. Although the Dirac equation managed to get rid of one of the major problems of the Klein-Gordon equation, the one dealing with non-positive definite probability density, it still suffers from one of the major drawbacks of the Klein-Gordon equation, namely the existence of negative energy states. Indeed, as I had said before, any particle which obeys any equation which is consistent with special theory of relativity must embody the energy equation E square equals P square C square plus M square C to the 4, and since this equation only gives you the square of the energy, such equations would always admit of two solutions, one with positive energy, another with negative energy. As we will see in a soon to come lecture, Dirac actually turned this existence of negative energy states from a liability into a huge asset, and managed to introduce a whole new concept of antiparticles, which used to be a new concept those days, out of this apparent problem. So that this disadvantage of the Dirac equation was not much of a disadvantage, it turned out to be an advantage. But that is for a later lecture. In fact, in the next lecture, what we are going to do first is take a look at what happens to these solutions when a particle is moving. For a particle at rest, the solution is simple enough. It will turn out that for a moving particle, the solutions are slightly more complicated, but really not that much more complicated. Well, there is one other major question that we will address in the next lecture, and that is about the Lorenz covariance of the Dirac equation. Note that we have started with the assumption that in order to be covariant, an equation must treat space and time on similar footing. So because we wanted a first order equation in time, we also demanded that the spatial derivatives also occur to only the first order. But that, frankly, is only the first step towards showing covariance. In order to establish whether the Dirac equation really is covariant, we need to show exactly how the quantities beta, alpha, etc. change, if they do at all, when you change from one inertial frame to another. We already know how the spatial derivatives or the time derivatives change, because we already know the Lorenz transformations. However, there's one more thing that we need to figure out. How exactly does a wave function psi change when you carry out a Lorenz transformation? We will answer this question in the next lecture, and we will see that as a bonus what we will obtain is exactly how psi behaves when you carry out a rotation. Rotations also being special cases of Lorenz transformations. And that actually will tell us that a particle which is described by the Dirac equation has spin 1/2, or an angular momentum whose projection is plus h cross by 2 or minus h cross by 2. But all this is something we are going to discuss in the next lecture. Bye for today.